Thank you very much, Ritz. Can anybody hear me, even in the back? All right. So thank you very much for the invitation. I'm very happy to be here today. And I'd like to talk to you about time of flight. I know that there are going to be some people that are some interesting speakers after me that are going to follow up and present more about time of flight. So I figured maybe it would be interesting to just introduce the field of time of flight and explain what it is. So in time of flight, first you need an object, you need a source of light, and then you need a target, usually a detector. And then finally a stopwatch. So if you're taking a pulse of light and you measure the time that it takes to go from the source to the object, the target, and back to the detector, this time is called time of flight. And is important because it allows you to determine the distance from the source and the detector to the object itself. Of course, this is not new. This has been invented, this contraption has been invented in 1849 by Fizeau. This actually measured the time of the true time of light, the speed of light, to a staggering precise number of 3.15 times 10 to the 8 meters per second. So, to many people, time of flight means 3D imaging, and this is actually true. With time of flight, you can determine the distance of the various features of an object. But you can also do other things. So you can also measure, for example, the distance between you and the wall, or this is actually done, for example, in telemetry. This is a product that was launched last year by Bosch, based on pads. And you can also perform proximity sensing. For example, this was launched by ST Microelectronics last year for determining the position of the head of a person using a cellular phone using time of flight. And actually, this product has been recently released and integrated in a cell phone. The idea here was to determine whether the person is using the phone or whether the person is doing something else with it, but ultimately I'm sure it will be used for other purposes within the phone. Of course, there's not only 3D imaging of interest, and not only proximity, but also potentially the avoidance of collisions, and collisions not only with other cars, but potentially with people, with young people particularly. And as you may know, there are 1.2 million deaths due to collisions between cars and people every year. So this is a technology that could be used for this type of application. Of course, you heard in the news that autonomous driving is gaining popularity. So is gaming, biometrics, and all these are actually potentially already using or will be using 3D time-of-flight based cameras. And the last example I want to give is not so obvious, is actually a positron emission tomography, where time-of-flight is actually used to gain insight of the position of the positrons that are annihilating with electrons for a reconstruction of images for cancer detection. So what do you need for time of flight? Usually you need ultrasound or microwaves or terahertz type of radiation. And also in our case, we are focusing on optical time of flight. So we are using visible or invisible light for reconstructing time of flight for 3D and for other applications. So the optical time of flight building blocks are three: the source, the detector, and the algorithms. I will not talk about sources and algorithms. I will focus on the detector in this talk. So if you're looking at time of flight detection, you have essentially indirect and direct time of flight. These are the two methods that are generally used and are generally available also in industry. You see most of the applications are actually using these two techniques. So let me explain in more detail what indirect time of flight is, or I-TOF. So in indirect time of flight, the idea is to send a continuous wave of optical optically modulated photons, and these are usually spread onto the target, represented here with a cone, and reflected back into through an optical system into a detector. Now, usually the calculation of the distance z is given by this equation that indicates the speed of light, the phase between the outgoing wave and the incoming wave, and the frequency of modulation. So essentially what you're doing, you're calculating over and over again the phase between the incoming and the outgoing wave, and you try to determine based on that the distance. So let me be a bit more specific. So the laser pulse is usually a square wave, and the receiving pulse is also a square wave. So essentially you're trying to determine the dephasing between the two. Now, in order to understand it a bit better, let me replace these two with sinusoids. If you do that, it turns out that by base multiplication of these two waves, you can show that you can compute after filtering a voltage that is actually proportional to the phase between the two, the outgoing and the incoming signal. And this is actually determined by voltage that is proportional to the cosine of the phase. Now, if you look at in a little bit more detail, you see that actually the relationship between this voltage and the phase is a sinusoid itself. However, you can, as you know, divide this into several arbitrary positions, let's say 4 positions. And if you're given this 4 position, you can determine the phase as a combination of these 4 voltages and a simple inverse transform, the arctangent transform. If you do that, actually, as a corollary, you can also get another information, which is the amplitude of the modulation and the offset. And now you'd say, well, I already know this, I don't care. But actually, that's not true, because you know the outgoing signal, but not the incoming signal. And knowing the amplitude of that signal, as well as knowing the offsets of such a signal, is very important information, because it tells you how reliable the information actually is. Turns out that the range is also limited by the frequency of modulation. So in other words, if you're looking at this equation tells you that the maximum distance that you can see before having a repeated measurement essentially is determined by the speed of light and the inverse of the frequency of modulation. So that tells me that essentially if I want to have a very high frequency of modulation, I will be limited by the maximum distance that I can go at. So, however, I also know that the resolution of the measurement is inversely proportional to the frequency f0. So, essentially, I cannot get both. Either I get a very high frequency and therefore I get a very high resolution, but then the range is going to be reduced, or the other way around. Actually, there is a way around this problem, and that is called a multi-frequency or multi-wavelength measurement. This is a very simple technique that allows you to actually extend the range at the same time to keep very high resolution. What about the accuracy? Resolution is one thing, and it tells me the minimum distance at which I can see in depth to objects. But the accuracy tells me how accurate this measurement is, how accurate the actual distance that I measure is with respect to reality. And it turns out that this is actually determined by the variation, the variability error introduced by the time of flight phase. But if you actually represent this in terms of the amplitude and the error on the voltage, then you will see this important formula that tells me that the accuracy is inversely proportional to the ratio between the amplitude of the modulation and the error on the voltage. So that tells me that it's very important to have a very large modulation, because that will give me the most reliable measurement. It turns out that actually there is as it is shown here, there is not only a relationship between the error and this ratio, but there's also a relationship between that and the frequency. So with the highest possible frequency, you can get the best possible error, given that you have a sufficiently high ratio A over sigma V. So this is essentially carving out the specifications we need for our detectors. So on the one hand, we need very high signal-to-noise ratio, if you like, and at the same time, we need very high frequency. So there are quite a few publications in the field. Besides our work in Canesta back in '99, there have been several people investigating several detectors that can be used with this approach. Now, the very first actually is it was based on CCD and was jointly, actually independently developed by Miyagawa and Seitz in the 1995-97. Then came a photonic mixed device known as a PMD by Schwarte and others, and finally PIN photodiodes presented by David Stopp and others back in 2010. So, of course, these are not the only three approaches. There are quite a few others, but I will, in the interest of time, just focus on these three. So the common principle to these three approaches is the following. You have light that is modulated coming in. There is some kind of gate, photo gate, and then there are ways of directing the charge that is accumulated from photo detection, either to one location or another. So when the voltages are such that the potential field is going in this direction, then you're going to transfer all the charges on one side. If, on the contrary, you are going to change the voltages at 180 degrees, you're going to reset the potential fields in such a way that the charges are actually going to go the other way. Now, why do you want to do that? The reason is very simple. You want to be able to have essentially the capability of measuring differentially, because all the light that comes to your detector all the time that is not modulated, you want to distribute equally on both locations, on both junctions, in such a way that you can then see it as a common mode voltage, and therefore you can easily remove it. Actually, you want to go one step further, and you want to prepare your signals, for example, by having 4 taps, in such a way that you will have essentially the sine and the cosine version. So in other words, you can easily compute the phi, the phase given by time of flight, as an arcotangent of these charges. This actually was done by Lange and others back in 2000. Now, why changing this approach? Well, actually what David did, he did something clever and introduced a concept that is known as PIN photodiode, which is well known in the imaging community, and is usually used to make sure that you can transfer completely the charge the photo charges that you have detected into a completely transfer into the junction here, thereby eliminating charge sharing. Now, by doing that, you can actually do it very fast. And since this technology is available in CMOS, you can construct at the same time a fast transfer and a very accurate complete transfer. So then you can apply the 4 taps type of approach, and you can obtain a very fast, very accurate type of detector. So this slide, actually provided by David, is a nice summary of what has been done in I-TOF in image in the last 15 years. And you can probably recognize here some of the authors that eventually led to detectors that are currently present in commercial designs. Let's focus on direct time of flight. So what do we do in direct time of flight? Well, we do something different but similar in a way. So what we are trying to do is to send a single pulse, to wait until the pulse comes back, and to measure the distance, the time, no longer the phase, but the time between the point of departure and the arrival of the photons. And the distance is essentially given by the speed of light, again, the time of flight divided by 2. Again, we do the same trick of dispersing light onto the object in order to be able to reconstruct a 3D image. Now, what are the challenges in D-TOF? Well, first of all, as we know, light is fast. And secondly, we also have the background given by the sun and other sources of light. How can we handle it? So we have seen it in modulation, that this is handled by using a 2 taps or 4 taps that eliminate automatically the common mode voltage, that is the correspondence result of this offset. But how do we do in a case of direct time of flight measurements? Well, the way you do it is there are several techniques. The first one was introduced by Jeremias and others in ISSCC 2001. So what they did is the following. They basically took 2 capacitances and a very fast shutter. The capacitance, the first capacitance, is actually used to convert the laser light, in this case, into a current that is then accumulated as a voltage given by this ramp. Now, in the second capacitance, that is used to actually subtract that original voltage that is due to the signal from the background. So the second time you do a similar exposure, but in absence of the laser light. So this way you can have the presence and the absence of the laser, and in both cases you can actually get the signal with and without the light, and therefore you can subtract the two and obtain a background-free detection. This is the chip that they designed, ultimately led to a chip that has 8 by 64 pixels. And the question is why they didn't go beyond the 8 by 64. And the reason is very simple. There is a very large power dissipation requirement for the chip because of the presence of all these devices on chip. And also because of the fact that the light is not being amplified in any ways, then it's essentially requiring very large power on the laser side. And essentially this is the main stopping point that made sure that the chips could not grow that much. So this and other problems being addressed again by the group of David Stoff, in particular Perenzoni, who designed a system that consists of an amplifier, a sample and hold, and a system for subtracting in real time the background illumination from the main signal. So this resulted in this switch cap circuit that, in interest of time, I will not go through, but actually stay assured it works. They built a 160 by 120 pixels with an accuracy of the order of centimeters with a 4-meter range. So essentially the whole power was in check, but you still have the problem of needing a very large amount of power to obtain the millimeter resolutions. So this is a photograph of the chip. It was published in 2010. So I think we need another idea. We need amplification and we need speed. And this new idea came with the another approach based on intrinsic amplification obtained in single photon detection. So this is obtained in a technique known as TCSPC, or time-correlated single photon counting. So the idea is very simple. You send a pulse, a laser pulse, and then you make a single measurement. Just this measurement corresponds to a single spat, or single photon detection. And then you repeat the experiment over and over again, and finally you construct a histogram. And that histogram has a centroid that corresponds to the time of arrival of the pulse that you're interested in looking at. So of course you need single photon detectors to do that, and a good system, for example, in solid state is to use a so-called secondary and tertiary electron given by an avalanche. So if you can construct a device that can avalanche, therefore you can get your amplification and you can get it really fast. So this is obtained either working in avalanche mode or in Geiger mode. If you're operating in Geiger mode, essentially you're operating above breakdown. Now, for a short amount of time, the diode is going to survive. And if you have ways of quench the avalanche, you can essentially construct a response that is proportional to the arrival of a single photon. If you do that, essentially you have for free your TC-SPC. It turns out that SPADs, or single photon avalanche diodes, have an excellent timing resolution, typically of the order of 50 to 100 picoseconds. So the combination of amplification and very good time resolution gives you the ingredients for an excellent TC-SPC technique. So this is something we looked at in an architecture known as LASP. In this architecture, we built a 128 by 128 SPAD array with 32 TDCs, or time-to-digital converters. Essentially, TDCs are chronometers that have a resolution of the order of picoseconds. And this allows, with a certain level of parallelism, to construct several measurements of the time of arrival, and therefore to reconstruct a histogram that you can then use for reconstructing your 3D image. So this is a micrograph of the chip LASP with the 32 TDCs that have a resolution that can be programmed from 70 to 500, 97 picosecond with a range that can be programmed from 70 to 500 nanoseconds. Now, what is the problem with this architecture? That the number of TDCs is too small. So essentially, the number of measurements that you can perform at the same time is only 32. So it turns out that you can do that 10 million times per second, but it's still not enough if you want to increase number of pixels. So this system is not really scalable. But the results are quite staggering. Here we achieved at 1 meter distance a resolution of the order of less than millimeter. And we could go up to 10 meters, actually, with a resolution that was far below the centimeter. So this is actually a linear response that you can see in the paper we published, ICCC 2008, and the error that we achieved. But we can go one step further and go much farther. So in this case, we actually made a measurement of 80 meters, and we still measured an accuracy of 7.5 centimeters. With a frame rate that was actually 10 frames per second, which is quite good. And the peak power was only 7 watts for the laser, and an average power was of the order of milliwatt at 850 nanometers. And notice that this was done outdoors, with a minimal use of filters. So this is good. This is all good. So in this slide, what I wanted to do is kind of show you a little bit of a relationship, a little bit of a comparison between the two techniques, indirect and direct. So looking at the depth resolution, we immediately see that indirect is directly proportional, is inversely proportional to the frequency of modulation. Now you do not have this problem in direct, because direct is only dependent on the precision of the single measure and on the resolution of it given by the chronometer. So this is kind of a point given to direct time of flight. If you look at the depth accuracy, actually you'll see, as we've seen earlier, that in the indirect system, it depends on the ratio between the amplitude of modulation and the error of the measurement, of the voltage measurement. And in direct time of flight, you have this M factor, which is the ratio between the outgoing photons and the incoming photons. So kind of similar. So many people keep on asking me, which one is better? Is I-TOF or D-TOF? And I think jury's still out. It's very difficult to actually make a conclusion here. So please don't ask me that question again. Well, or please do if you want to know. But the point is that essentially, it is dependent on the application, the amount of power that is available to you, the potential, the fact that you're using indoor measurements or outdoor measurement, the cost that you want to have. So there are a lot of variables that come into place. So it's not really a very easy way to, there's no single answer to this question. So, question is, okay, we've seen that TC-SPC is a good method, but how can we make it faster? Obviously, we cannot make the laser go faster. We cannot make the TDCs or the SPADs going faster. So maybe we can parallelize. So that's what we tried recently, where we replaced a single SPAD with an array of SPADs. And then we essentially connected each of these detectors, each of these SPADs, to a TDC. Independently, therefore, having the ability of measuring the time of arrival for each one of these detectors. Now, what is the advantage here? Essentially, the total number of photons is the same, but the capability of doing independent, simultaneous, massively parallel measurement is increased. And actually, if you use statistics, you can show that lasers do not have completely IID photons coming out, and the PDFs, the probability density function, is actually not the same for all the photons. So you can have some interesting analysis, and it turns out that this is actually an example that we did and we recently published in Optics Express, where we show that if you have multiple photons available to you and the capability of having access to an algorithm to combine these photons, if you know what the PDF of each photon is, then you will be able to get a better insight of the original pulse. And this is actually done in two of the chips that has been recently published, one in ISSCC last year and one in NSS a couple of years ago. And there's one that is actually coming in ISSCC next year, presented by our group. So the idea is to have a very large number of SPADs and a certain number of TDCs available, and therefore being able to use the statistics, as I mentioned earlier. So I'd like to conclude the talk presenting maybe a few challenges. So I'd like to summarize this in four tens and 1K rule. So essentially, I think that we're certainly going to get to 1 or 10 megapixels at some point. We're certainly going to have a 10 picosecond resolution, a 10 micrometer pitch or less, and a 10 milliwatt or less in terms of power of the device. We also think that we're going to reach frame per seconds of the order of thousands. But I think the most important thing is that most likely these detectors are going to be of the new generation, fully digital, low cost, and potentially small. So in the interest of time, I'd like to just give you some discussions about maybe some of the future developments that could be happening. One is combining 2D and 3D. This is work that was published in ISSCC a couple of years ago and also championed by Eric Fosson. But I think the most important is really the trend of going to 3D. In 3D, essentially, you're going to get away from a planar integration and going to a completely 3D chip for 3D detection. This is an example of a chip that we are going to present in a week, actually. And this is probably the first SPAD, backside illuminated SPAD in 3D, integrated in 3D with TDCs on the other side. Of course, variety is very important. I think variety is what gives the utilization of 3D time-of-flight-based techniques based on the different applications. So this is my last slide, and I'd like to kind of summarize what the message that I'd like to give to you. And one is that time-of-flight images are really here to stay. 10 years ago, that was not the case, but now I can really confidently say that. 3D vision applications are much more than what one can think, and single photon detection is actually much more than a curiosity. And I like to show this image as what I see the next generation 3D camera would be. And actually this work, and what I presented to you, my This would not have been possible without these people here, and without those that have funded our work in the past 10 to 15 years. And with this, I'd like to thank you very much for your attention, and if you have any questions.